No, I have no idea. Because these come out.
I mean, I don't feel like a high party because I feel like the work issue. Angel wants it because he believes that someone doesn't go. That will go past that. He needs to.
What is it?
I just like I created work. So it's just a simple form. So I feel like I'm an idiot.
I feel like you would just be the owner.
Yeah, because somehow I just can't do it.
So you press go live.
I'm just thinking like skeleton. Yeah.
I can take a look at it now, but I don't know.
You mean the repo or yeah, go ahead.
Okay, but
you can create over. What the?
oh yeah, I took a picture for it. I just like style it. Add the class to whatever to get my
This is so fancy.
No, this is just the oh yeah, and then like we get the wrong like so. Organization account name.
I
sold my soul. Unfortunately, it's like you know
no, I like podcast is better than trading.
on Friday, and it just happened that they opened history museum. They just do yeah, so they just do so that's a t-shirt, and there's a guy who's giving the tour. He's like, give me special attention. He's like,
You have a
yeah, sure. Do you want to chat?
because you already started working here, so like, we're such a loner. Yeah, so I go to the companies, I'm like, nah, no, oh yeah, you feel like, I don't think so. QR code. Start putting QR codes. And you scan it and you lose all the bitcoins. And you lose all the bitcoins, right?
That's a cool one. Yeah, exactly.
This is when you need professional.
Yeah, we're having trouble with OBS.
GDP. Anybody can learn.
What I would do here. Okay.
You can just switch cameras and do that. And then
Anything
Exactly.
Hello. Can you hear me? Okay. Is there a? Yeah. Lightning touch. You tell me. Okay. Hello everyone. Sorry for the delay. My name is Jose. Welcome to the first of the second season. The first workshop about transformers using OpenVino. So, how many of you here are new to machine learning? Good. How many of you have any kind of experience with machine learning? Nice. How many of you are professional machine learning engineers? Your job involves that. Great. So it looks like this might be very interesting to all of you. It doesn't matter if you have like many years of experience working with machine learning and AI systems, or if this is the first contact that you have with this kind of systems, you've been curious, you want to learn what's all about. So this is a great moment to step in because there's a lot of things happening in the industry. And I'm gonna focus on a particular machine learning architecture that's called transformers. And we're gonna have a few sessions about it. Now, before we start, so this is the agenda for today. I'm gonna give you a quick tour around OpenVino resources. Mostly I'm gonna show you a couple of sites and GitHub repos that will be very useful for you on your journey of learning, machine learning. If you don't know OpenVino is Intel's framework to deploy machine learning models for inference in any kind of hardware, GPU, CPU, even embedded devices. Then I will be showing what you need to do to join a challenge where you can win some prizes. These prizes are provided by Intel, and one of the prizes is going to be actually an Intel Arc GPU, A770, so that's great. Then I'm going to show you 6 different models that do 6 different things, but that have something in common. And then I'm going to show you what they have in common, and that's going to be it for today. Please, if at any time in my presentation I am not being clear with the things that I'm saying, if you need further explanation or if you have any question that might be relevant to the moment that I'm presenting or talking about something in particular, please raise your hand and let me know and ask me your question out loud so that I can repeat it and the people on the stream can know what we're talking about. Okay, cool. So, what is OpenVino? So OpenVino is a framework provided by Intel that allows us to convert and deploy machine learning models for inference on any kind of hardware. And when I say any kind of hardware, that includes CPU, GPUs, discrete and integrated, VPUs and FPGAs. And it also can run on any OS of the common OSs, Linux, Windows, Mac. They provide a lot of resources that can be useful. In particular, I'm going to show you here this repository that's OpenVino notebooks. All the examples that I'm going to show you today come from this repository in particular. Who here is already familiar with Python? Well, we're going to be using Python today, mostly because it's the industry standard nowadays to do machine learning. And inside the Python ecosystem, there's this thing called the Jupyter Notebooks, which is an environment, an interactive environment that allows me to write and execute code at the same time. So it's very useful if we are doing any kind of scientific tasks. And so that's how we're going to be interacting with OpenVino today. The other important site that you should be aware of is OpenVino's documentation. If you visit this particular site, you will find a lot of resources that will take you from the beginning, from setting up in any of the environments that you want to be working on, so that you can get familiar with OpenVino, learn like the very essentials, how to run it, how to use it for inference, and then learn a little bit about some more interesting stuff, some more advanced features that will allow you to leverage the performance of your hardware and run your machine learning models in a very efficient way. Now, why is this important? Well, we all know that machine learning needs a lot of compute to work, right? And that means if our project becomes successful, it's gonna start costing us a lot of money if we're running it on the cloud. So tools like OpenVino make it actually very efficient to scale, while not necessarily having to pay the huge amounts of money that we would need to be paying if we didn't convert our models, if we were using the same framework that we used to train our machine learning models for inference. Because those are two very different tasks. And for inference, what we want to have is a fast, accurate response, but not necessarily leverage or have to have the most powerful hardware every time a user is wanting to get a result from our model. So all of these details, you can get a little bit of knowledge here. There's a lot of interactive tutorials and some documentation about the notebooks that we're going to be using today. The notebooks are organized in 4 different parts. The first part, and if you go to the repository and look at the notebooks here, those that start with 0 are just like very basic intros. The 100s are demonstrate features about OpenVino. How do you convert models? How do you train models? How do you leverage the different hardware devices that might be available for you? How do you run a model on CPU, on GPU? How do you optimize such models? Then the 200 series are the demos. These come from interesting papers or products that have been deployed in the wild, and the OpenVino contributors take those models and create examples with those models. So those are the ones that we're going to be visiting today, and I encourage you to come to this repo, take a look at what's available, and just run them. It's a great way to start getting your feet wet in this machine learning world. You're gonna start from the application side instead of from the very theoretical math side. I myself am a software developer. I don't come from a data scientist background, and as such, I feel very that is very gratifying to see the things actually delivering results from the very beginning, and not necessarily having to go through all the journey of learning the math, and which I eventually did, and I encourage you to do as well. But it's not necessarily on this day and age the only path that you have to get into machine learning. 300 series are about optimizations, and 400 series are some demos regarding live demos, live interactive demos. Most of them are using a webcam for that. So that's where we're going to be today. Now, there's another very interesting repository that's called the OpenVino SU, the Open Model SU. So here you will find even more models that are already available for you to take and use in your applications. You can look at the licensing in each model, but most of them are either MIT or Apache 2, and that means that you can use them for commercial purposes if you want, as long as you follow the guidelines of each of the licenses. If you go in this repository into models, you're going to see basically two major categories: public and Intel. The ones that you will find inside Intel are officially supported models to run on OpenVino. That means that the team at Intel have converted, tested, and made sure that these models are operating within the parameters that they were operating before being converted into the OpenVino ecosystem. The other one, the public one, are models that not necessarily have been completely validated, but that are known to work on OpenVino. I have personal experience using, for example, DeepLab in a production environment with no problems. So your mileage may vary, but you will see that there's a lot of options here. Some of them will have a very explicit name, like single human pose estimation, that tells you what the model does. Some of them you might need to be a little bit familiar with what everything, what each model is doing, and what the purpose of each version of that model is. But it's not that hard. Most of them have a very descriptive name. So I invite you to come take a look at the Open Model SU from the OpenVino toolkit repository at GitHub. So those are the three main resources that I want you to be aware of. 1, the documentation; 2, the OpenVino Model SU; and 3, the OpenVino notebooks, which is how I learned OpenVino and how I encourage you to learn and maybe even contribute in the future if you're interested. Okay, so there's the QR to the GitHub repo if you're interested. About the challenge. So thank you, Intel, for sponsoring this series of events. We're going to be running 4 sessions for this. Intel will be providing prizes for the top 3 winners top 3 participants. The rules are not published yet. I will publish them tomorrow afternoon in the Discord channel. Join the Discord. There's the QR in the bottom right, so that you can join the Hacker Dojo Discord, go into our channel, and then you'll be able to participate and maybe win some Intel hardware or some goodies. I don't know. Most of the work you will be able to do from your computer, but if you don't have a workstation, Intel also provided us with 2 NUCs that are already set up there. We'll be setting up a system for you to schedule and come and make use of that hardware for free, free of charge. Just come, join the Discord, follow the instructions to reserve your spot, and feel free to come and use that. And while you're doing that, tell your friends about Hacker Dojo and the things that we're doing here. This is an amazing place to come, learn, and share with your community of technology enthusiasts. So I invite you to spread the word about that as well. So let's go and jump into the first model. BERT. Is anyone familiar with BERT? I'm going to tell you which model, very similar in nature, you are familiar with. GPT-4. Who's familiar with GPT-4? ChatGPT. Who has heard about it? What do you do with GPT? You ask a question and it responds, right? Okay, so how does it work? I'm going to show you the first demo here. In this particular, can you see that? Is that too small? Is that better? Okay, so I'm going to show you the last part of the notebook, and then I'm going to show you more or less how each and every notebook is organized, so that you get familiar with how it is. Here, I'm passing the URL from for OpenVino from Wikipedia, and I can ask a question here. For example, what is OpenVino? And then I can answer. It's the Open Visual Inference and Neural Network Optimization Framework, right? Okay. Where is OpenVino available? Well, that's the license. What hardware is available for OpenVino? OpenVino toolkit, which is supported by Intel. It's not answering my questions very accurately. Where can you deploy OpenVino? Intel hardware. Okay. What Intel hardware is supported by OpenVino? It's not answering what I wanted to answer. But basically what this is doing is it is taking the context that is inside this website, this text. It is mapping this text into a latent space. That means it's understanding it. And then when I ask a question, it's mapping that question into the same space and trying to find the closest piece of information from my context to provide me with an answer. That's like on a very high level what's happening. It's interesting because you can unlike GPT-4, even though the answers are not that verbose or fancy, this is very useful if you're working in your own app. This is using a model called BERT Small that can be actually deployed to hardware that you can run. I mean, I'm running it on my laptop along many other stuff, right? Well, we know we cannot run something like GPT-4. There's a version of GPT-2, that is also available in one of the demos in OpenVino. And what I find very useful is this ability to just download the context directly from the internet. TensorFlow. I think I'm going to restart it because it's giving me very random answers. Okay, so that's question answering. That is the first task that I'm going to show you today. Questions? No? Question answering? No? Everything's clear? Cool. Second task. We're going to talk about visual question answering, and that means I'm going to give you an image as a context, and then I'm going to ask a query, and that query is going to be text, and I'm going to learn stuff about that image. How does that work? Well, here's some explanations about what's actually happening. For example, in this second graphic here, you can see that when someone asks the question, how many bridges are there, and provides this image of a river with several bridges going on top of that, it actually separates that query into several things. The context, which is the image, and then the type of answer is going to be a number, and then the object that it's looking for. And it's going to be bridges, right? So it's going to encode that, and it's going to provide me with an answer. How is that useful? Well, I'm going to show you an example. I'm going to go all the way down here. And this is a model that does three things. It provides me with the ability to retrieve images. That means I can search for images and find matches for the thing that I'm searching. The model is called Blip, and it was actually developed and published open source by Salesforce. The second thing that it can do is it can summarize or give me a description of the image that I'm showing it. So for example, here, a man and a dog are reading a book together, right? That's the little example. And number three, and what I find most interesting, is I can ask a question about this particular image. And so that's what we're doing here. If we do the image captioning, the description is a dog is sitting on a beach. It's kind of what's happening there, but it's not everything that's happening there. And then we can ask some questions like, how many dogs are in the picture? Okay, 1. I find it more interesting when I ask it, when I ask the kind of questions that are not directly evident, and that can be maybe more interesting. So for example, this is me with my dog in the streets of San Francisco. One of the things that I find interesting to ask, for example, obviously I can ask how many people are in the picture, how many dogs are in the picture, but I can ask more abstract stuff like, where is this happening? And the answer is on the city street. Okay. what city is this? And it can tell me stuff like New York. It's not New York. Is this San Francisco, San Diego, or Mexico City? If I give it answers, it provides me with a response regarding that answer. I find that very, very interesting, because not only if I don't provide an answer, a possible answer, it will give me what the model thinks that answers best that question. And that means because it has an incomplete model of the context that I'm providing, the closest thing that it can find from its training data is New York. New York City is a city, mostly flat, with a bunch of buildings. And that's what you can see in the picture, right? I find that very interesting, because if I say, no, let's gonna limit the scope of the answers that I want you to give me, then we're conditioning the model, we're guiding it. Some people call, when you do that with prompt engineering, you're steering the model, right? You're steering the conversation into giving you something that's within your control. And this, we know, can be very, very useful. So this is one of the models that I find very, very interesting. Mostly, yes.
So just out of curiosity, so if you ask and give the New York City and San Francisco,
Yeah. So most likely, it will say that it's New York City, because with no conditioning, yeah, it says New York. With no conditioning, it assumes it is New York. But if you remove it from the possible answers, then it gives you the closest thing, which is San Francisco, which is actually the correct answer, right? I don't know, I find it interesting, because there's nothing there that says San Francisco, California, nothing. It's just how it looks, right? And one can say, okay, maybe there's a lot of images tagged only as San Francisco. And then we can ask, in what continent is this happening? North America. Okay, so it knows stuff about San Francisco. In what country is this happening? USA. Is the model aware of the things that it's answering? No. What's happening? It's mapping my questions into a set of data. A lot of this model was trained with a lot of data, and it is providing me with the closest things that are related in this latent space. And to understand what a latent space is, imagine that you translate the word or the image into a set of properties, right? So when I am asking about a place, there are some things that are related, like for a place. For example, there's a name of the city with certain characteristics, certain features. Cities are related to states. States are related to countries. Countries are related to continents. And all of that information is present, or at least is close to the information that's extracted from that image when it runs through the encoder. So for me, that's one of the things that I find most interesting in this like newer wave of vision processing, computer vision. Convolutional neural networks took us half of the way there, but now with the transformer technology, we are getting all the context at once, and we're getting closer to what I think is more interesting in terms of intelligent systems. Next, zero-shot classification. Who here knows what a image classification model does. Anyone? What does it sound like? No? Well, an image classification model, basically what I do is I show it an image, and then I ask the model, what is this image? And then if it's a dog, it's going to tell me it's a dog. If it's a muffin, it's going to tell me it's a muffin, right? Traditionally, how those models are trained are, I take a lot of labeled data, and that's the key. And what does labeled data means? I have a bunch of images organized in separate folders, each folder belonging to a separate category or class. For example, all the dogs are together, all the cats are together, all the cars are together, or all the motorcycles are together. And then I iteratively feed that data and with the labels into a training group, and the model will learn to predict the next time I show it an image that it has never seen, which is the category that has the most similar features to the new image that I'm showing. So everyone following here? So that means that if tomorrow I have a new category, a new class, what I need to do is I need to modify my neural network, I need to add a new class, and I need to retrain it, at least part of it, part of the neural. So that's the traditional way of doing classification. Here we have a model called CLIP, which means contrastive language image pre-training. This model was developed by OpenAI, if I'm correct. I'm
Yeah, it was done.
Yeah. And it is trained to understand images by itself. The key here is that it is trained showing it images with available captions from the internet. Like images accompanied by text available from the internet without any human intervention. They just showed it and feed a bunch of data into this model until the model learns to make associations between certain kind of features in the images and text. And now what we can do is we have a classifier where we can show it new classes and ask it which of these classes represents is the best description of the image that I'm showing. And again, I'm going to show you my picture in San Francisco. Okay, and here I can is that a dog, a bird, or I can ask if I'm in a beach, at a city, or at the forest, right? And it's going to show me that I'm at the city. I can ask who is the main subject here. Like, is it the street? Is it the dog? Is it the person? Or is it a car? What is more important? It's a street. Okay, and then if we remove it, Lola is more important than me by a lot, right? So I find that very, very interesting. How is this useful? Because you don't need to, not necessarily need to retrain a whole network to add a new class, right? If you have a sufficiently trained model with sufficient context, you can deploy it once and use it for several purposes throughout the course of its life and in production. Obviously, there are some, it is trained with the images that are most representative in the internet. That means from societies that are connected to the internet, in English speaking mostly, etc. So there are some constraints. Most of them are pictures, some of them are illustrations. If I want to show it a document and ask it like, what does this document say? It cannot answer that, right? Because there's not a lot of available documents with accompanying description about what's in the document available in the internet in this particular format that were used to train this particular model. But if I want to deploy this to an app and then just, I don't know, create a game or whatever, it's very easy to do. And so I find this extremely interesting. The same model can be used to what's called saliency. Saliency? How's that pronounced? I think I've never said it out loud. Saliency or saliency segmentation, right? Basically what it says is, I'm going to ask this model, the same model, same pre-training, with a different head, a very abstract question, like who developed the theory of general relativity? And within that context, it shows me which region of the image is more interesting, which region is hotter for the model, and which region is colder, which is the blue. And it's interesting that it shows me which is far away from the question, and that's not the background, it's the other people in the picture, right? And that's because how this model was trained. It was trained with something called contrastive learning. And what it does is you train the model, you condition the model to put together things that are alike and to be very far away to things that are different, right? And that depends on in what dimension are they alike and in what dimension are they different. So that's also very interesting. You can see that particular notebook here, and learn a little bit about what it does. It's basically what I described. What the model actually does is it takes the image, it takes some random crops, and then iteratively encodes that random crop and compares from the original image if it's closer or further away from the image itself, from the query that I'm asking. And so if it's closer, it paints red. If it's further away, it paints blue. You can see it in action. It's actually not very fast, but you can tune it. Here, for example, if I provide, let's see, let's do this. Who invented the time machine? Okay. Let's see how it does. Now, this is running 300 cycles of cropping pieces of the image and comparing how close is this crop from the question that it's being asked. It's not very good. That one, let's see a different picture. Let's try this one. think the notebook crashed. Okay, I'm gonna try to restart and run it again, and see if you can see it later. Then the next one, I'm not actually gonna run it live, but you can.
Okay, there's some question.
Yes,
So like the out is a heat map, right?
it is a heat map.
So
Yes.
okay, so I was wondering, like the model did okay because like I mean
Yeah.
it's better than blue. I mean the pixels were like better than blue, but like yeah, it was a little bit off.
Yeah, it's but something weird happened because it kind of like got stuck.
And the other question is like, should the query be relevant to that image? If you ask it,
If you ask something that's irrelevant, it basically paints everything blue.
oh, okay.
And you can try that again if you want. I'll show you how to interact yourself with it. You can do that here in those machines, or you can do that in your local computer. So this is, for example, running against the Einstein picture. Let's see. I'm running all of these models at once, and that might be stretching it a little bit for that hardware. Well, everything that I'm running is on one of those nukes. I'm just accessing it via the web browser.
So these models are trained on images as well as text? Because I'm just
Yes,
curious how
so-
it is answering the question.
So this is leveraging a model that's called CLIP. From OpenAI. This. And that's what it does. Connecting text and images. If you're interested, read a little bit about how this is trained. But this is the gist of it. It shows texts and captions to a transformer model without anything else. And now the key, again, something that we're seeing again, is we are not training with labeled data per se. We have pairs of captions and images, but that doesn't necessarily mean that it's an accurate description of what we would be expecting if we were training a classifier. It's just a piece of text and a related image.
So when we throw the caption and when we throw the question, it's gonna divide all the words, take it as a caption and search, or?
So, not quite. What it does is, if you see there's two paths, right? It takes the image on one side, and what it does is it chops it into little pieces and then encodes it. And by encodes it, I mean it creates an embedding that's a representation of the features in the image, right? So that's on the top side. And then on the bottom side, it converts the text into tokens. Now, what are tokens? Tokens are basically representations of words or sounds, and a tokenizer is trained alongside with an encoder, right? So it transforms the tokens, the words into tokens, and then encodes those tokens. And what do we get? We again get a vector that represents the features that are present in that sentence that I passed, right? Now, if during the training process, somehow we combine the vectors that come from the image domain and the vectors that come from the text domain, then we're mapping both into the same latent space. And then we can use the transformer itself, which is an attention mechanism that will create relationships between what's present in the image and what's present in the sentence. And it will learn, the more I show it, it will learn like, oh, this group of pixels that look like this, it's a dog. And then a dog, it's a pet. And a pet can also be a cat. And so it starts learning those intrinsic, it starts learning those features from the intrinsic information of the pairs of images and text that I'm showing. Does that make sense? Now, I'm super simplifying the work of many talented people. It's way more complex than that, but I'm trying to bring it down to here. And so, if you see in this picture, I get a vector for the image, I get a vector for the text, and then if I multiply those, then I get how they are related to each other, and that's called attention, right? And then this is frozen, and when that is frozen, then I can do other stuff, like for example, show me the interesting regions that are related to this particular query.
So when we give them questions, they do the same thing, tokenize,
Yes, so
find the similar stuff.
So it's an iterative process where I think the process is described here somewhere. Yeah, here. It computes the similarity between the query and the image. So who invented relativity, right? Who developed the theory of general relativity? And I'm showing this image, right? So it's somewhat similar because Albert Einstein is there, right? So there's a similarity score, and that's your baseline. And then 300 times, I take a crop of 50 pixels by 50 pixels randomly from some part in the image, encode that little square, and compare the similarity against the sentence. Again, the same sentence. So what do we get now? Either we get a closer similarity, if that is closer to Einstein's face, or we go further away. If that's like a person that has nothing to do with Einstein, it's gonna be like, no, this is not Einstein, right? Or if I get background, it's just neutral, right? It's irrelevant. You do that, you adopt all of those, and then you create a mask. And that's why, the saliency map looks kind of like squares, because that's actually what it is. It's a bunch of squares overlapped on top of each other that says hot, cold, hot, cold, hot, cold, hot, cold. 300 times, this is what you get. Did I answer your question?
Yeah.
Okay.
Thank you.
So this is let's see if it can give me my answer. No, it's not working for me. Maybe after the session's done. Okay. Next model, stable diffusion. Who is familiar with stable diffusion? DALL-E 2. Yeah, kind of the same idea. Stable diffusion, DALL-E 2, Midjourney, all of those models are not really a model, but an assembly of models. And it's a pipeline that allows us to create, to generate images out of a text description, right? How does it work? I think this is too small. I'll try to make it a little bit bigger, but I don't know if you're gonna see some of the words that you've heard me saying this afternoon, because the concepts are the same. You're gonna take the tokenizer and you're gonna use the same encoder that we used from the previous model, the clip model, to create a text embedding, right? And then on the other side, we're gonna generate random noise. So just noise, Gaussian noise, the size of the image that I want to generate. And then I'm gonna use that noise in a model conditioned with the query and I'm gonna say, if this is noise, and this noise comes from an image that matches this description, remove a little bit of that noise and take me back to the image that fits the description. And I'm gonna do that a number of times, again. That's the reason why I'm not running this particular one, because it takes several minutes to run on my machine in particular. But it does that until it finds something, until it completes the n cycles that I conditioned it to, or until it decides that it's good enough, right? So, for example, in Stable Diffusion, in the example that I'm showing, this is the description. Valley in the Alps at sunset, epic vista, beautiful landscape, 4K, 8K. All of those are pieces of captions that kind of go along with images that are of the style that I'm trying to find, right? And this is the image that it generates. It looks like a high resolution image of a landscape. It's completely artificial. It's like this amazing view. And it's also conditioned not only positively, but negatively, which is very interesting. I'm also removing like all kinds of frames, borderlines, text, characters, duplicates, error, out of frame, watermark, low quality, ugly, deformed, blur. All of those are terms that I'm used, like if the things that you're generating model fits this description, you're going in the wrong direction. Take me to where this doesn't exist as part of the description, right? So again, I find it interesting, the mechanics of how you create an image, right? You give it a description, map it to a certain space that describes the features, that, let's say, expand that description into a set of features, and then I provide noise and put them together and say, from this noise, take me to this image. If I run it again, I get a different image because I start from a different noise. If I provide the same noise every time, I get the same image every time. So that's also interesting. Questions? No?
So how does model is built?
This is an assembly of different models. On the encoder side, it's actually the frozen clip text encoder, which is clip is the model that we use for zero-shot classification, like this, or the salient, I don't know how that's pronounced, sorry. Salient CMap, which is this. Remember that this model has a text side and an image side. So I take the text encoder and keep it as is. And then I take a unit. A unit is a segmentation model. It's basically a model it's a convolutional model that takes an image, shrinks it into a smaller space, smaller dimension vector, and then expands it again while bringing back some of the original features. I'm not being clear, so I'm going to show you a diagram of how the unit looks. It is that. So on one side you can have, let's say, a ResNet, right? That's creating a feature map, and then on the other side you go like in the opposite direction until you end up with an image that's of the same size or of a similar size, and then you connect some of the intermediate layers from one side to the other so that you preserve the nature of the original image. And what that gives you is a segmentation map, right? So using that architecture is how I generate a new image that starts from the random noise and the embedding. These are literally concatenated and fed into the network. And then there's a variational autoencoder, which is a generative model where I provide a vector and it gives me an image. And this is also trained, this is what's actually trained during this iterative process, if that makes sense. An example of a variational autoencoder is, I think, this one. This person does not exist. It's not there anymore. There used to be a website where that showed you a picture of a person that didn't exist. And every time you visit it, it's going to be a different picture because it's a picture that's actually generated there. I don't know if I answered your question somewhat. I can point you to more detailed resources after the session if you want. But this is basically stable diffusion. DALL-E, Midjourney, very similar architectures. And finally, my current favorite is a model called Segment Anything. This is a model that I have spent hours, and I'm not lying, hours playing with. Because I am impressed of the amount of information that can be present in a simple image. And how the very talented people from Facebook research created this model. And I'm going to show you how it works. Let me see if I can. I don't remember if I left it running. Nope. Let's see. Okay. Let's try again. I'm trying to start the interactive mode where I can upload an image myself and use my mouse to show that, but apparently it's not working. So I'm going to take you to the official site. Again, this notebook actually works and works really well, but I'm running everything at once, so maybe it's too much for my little computer. Yeah. Okay, so what this model does is it finds all the different objects that are present in an image, and it can generate either an automatic segmentation or an interactive segmentation. What's the difference between those? An automatic does this, what I'm showing. Like, I feed an image, and it finds everything that it can find. It segments everything that it can segment. And so I don't really know what I'm gonna get. But the more interesting part is on the demo. So this is the official demo by Facebook, where it literally shows different. I did it wrong. It assigns each pixel with a particular class that belongs to a specific object, and I'm not sure what I'm doing wrong because it should be segmenting the dog. Let me see if I can again run it on this. And I'm a little frustrated because I have been running several times today. Okay, here we are. Okay, so I'm gonna upload the same picture of me with my dog in San Francisco. It's not playing ball. I apologize. The interesting part about the segment anything model is that there are several ways where I can interact with the model. One is I can click, select a point, and it will create a mask around the object that I clicked. For example, right now I clicked on my sunglasses, and it's particularly slow. I don't know why. Maybe because I'm overloading the little machine. But it will create a mask of the object that I'm selecting. I can also provide, for example here, I can also provide a window of the positive things that I want it to mask, and then a negative point. And the result of that is, for example, this, right? It separates the wheel from the tire, and so it creates a mask for the wheel itself. Here, for example, I selected my sunglasses, and it created a mask of my sunglasses, right? If I select the dog, it will create a mask of the dog, etc. I don't know why it's being particularly misbehaving, slow today, but again, you can go and experiment with it yourself if you're interested. So that's the segment anything model. So what do all these models have in common? They are all based on something that's called the transformer architecture. Machine learning, neural networks in particular, started with what we used to call multi-layer perceptrons. And those were just layers and layers of neurons connected to each other, densely connected. That can be useful to learn some functions. After that, but it proved that it was very hard to train those kind of models, basically because we didn't have the computational resources or the data or the means to train all of those models. And the more layers that I added, it exponentially grew the number of parameters that needed to be learned. And with that, the need of data, the volume of data needed to train such models. So it was, from the beginning, limited in what it could be done. Now, about a decade ago, a new revolution with neural networks started. And that was the convolutional neural networks. I don't know if you remember the first model that Google deployed, I think it was 2013 or 2012, where you could actually upload a picture and it would tell you, this is a cat. And that was revolutionary at the time, right? That was powered by an architecture called convolutional neural networks, where instead of learning a separate weight for each pixel relating to each other pixel in a somewhat linear function. It could learn the weights for a limited set of filters, limiting the number of parameters that needed to be learned to much less, and allowing for the development of a lot of new algorithms and a lot of new architectures and techniques that took machine learning to where we were, where we are today, mostly on the computer vision side, but also sparked some new development on other tasks. One particular task that stayed behind was natural language processing. And for the longest time, the neural architecture that was used for NLP was recurrent neural networks. And the reason for that is that a recurrent neural network is a network that's designed to learn on sequences of information, like language. A language is a sequence of words. The problem with recurrent neural networks is that, yes, they learn on sequences, but they don't have a very long-lasting memory. So by the time that the last word of the sentence was fed into the network, it was very likely that the first word was already forgotten by the network, right? So it has temporary context. They were slow to train. They're very hard to train, but they allowed for some development. And then in 2017, some very smart group of people published a paper called "Attention is All You Need." And I think that this particular paper is what sparked the next generation of AI revolution, and it's what we're living today. Sparked again with applications like ChatGPT, DALL-E, things that are becoming closer to the end user to be able to use, and not necessarily to mad scientists in a lab somewhere in Silicon Valley, right? So the innovation here is called the transformer. And the transformer is this not very simple block on the left, but that's the basis of all the architectures that I showed. All the architectures that I showed have the same structure, exact same structure. And all of those share one thing in common. They are trained with very large amounts of data, but mostly in an unsupervised manner. So for example, GPT is trained by showing it sentences and masking words and making it predict what was the word that was removed during the training phase. And they do that with the whole internet, literally, to train it, to learn a very, very large network. But it will learn to find relationships between the different positions of the language. If you feed it text in different languages, it will be a multi-language model like GPT-4. GPT-4 is multilingual. If you ask in Spanish, it will respond in Spanish. If you ask in Italian, it will respond in Italian. Whereas in GPT-3, there was a machine translation layer before, because it was only trained in English. So there was error on the input and then error on the output back, because there was two machine translation layers to interact with it in a different language. So this is very, very interesting. Attention is All You Need is not a very hard paper to read. It is disguised as a machine translation paper because that's the end application. But it actually sparked a lot of development and the new generation of developments of architectural models. And what is now known, or what we're trying to make the more common way of using these kind of models, which is zero-shot transfer learning, which is I take a model that's been pre-trained by someone else, and I do very little to adjust it for my application. And that means that I don't need vast amount of data because I can leverage all the knowledge that's already there, which was very hard to do with all the previous architectures. So if this is interesting for you, this is what this series is going to be about. It's going to be about transformers. Next session is going to be mostly about understanding what a transformer is. So it's going to be a little bit more technical than today, not a lot, but it's going to be a little bit some code in there to understand how the transformers are a communication mechanism, basically, right, between the data. So that's what I have for you today. Again, what I find interesting about transformers is how they are able to find information in the data, relationships among the data, how data relates to each other, and have long range dependencies, or in other words, longer term memory than previously with other networks. And a particular property that allows to train these very large models is that it's highly parallelizable, unlike recurrent neural networks, that because of their sequential nature, you cannot actually train very large networks. They're painfully slow to train. But now transformers are very efficient. They started being very large models, and as always, very smart people are doing very smart things to shrink them. And I don't know if you saw, for example, Google I/O announcements last week. There's going to be a version of their language model that's going to be able to run offline on a mobile device. So we're going to go from something that needs several servers to run to your tiny little ARM computer in your hand. So I find that pretty amazing. So if you want to try it, if you're here and you're connected to the Python Wi-Fi network, you can go to alpaca.local/8889, and the password is OpenVino. If you want to try it at home, I created a Docker image based out of Intel's repository, and that's the command that you can use to run. If you have an Intel GPU, actually I didn't put the complete, let me, notebooks, stop Docker. So if you have an Intel GPU, either integrated or discrete, use this command to run it instead. I'm going to put this page on the Discord so that you can follow it. And I think that's it from me. Thank you. Questions? No? Yes?
I just wanted to know where to access those slides.
I will post them on the Discord. And I will create a repository as well, where I will be uploading some examples. And on the Discord, I will also be posting the rules to join the challenge tomorrow. Okay? You will have, so there's going to be 3 separate challenges on workshop 1, 2, and 3, and then on the 4th one, we're going to give the prizes and announce the winners. It's not about who's going to be fast. So that's why I'm taking a little bit more time to publish the rules, because the more straightforward challenges are about who's the first one to solve something. And I'm more interested in seeing who is the best, what is the best solution to a certain problem that I can present, or the most creative solution. I'm trying to make it as objective as possible, although there might be some subjective judgment that we will find a way to democratize or make people vote or something. I don't know. So I have a few ideas of the applications. I'm gonna develop the rules and publish them tomorrow, and then you're gonna have until the end of the sessions to submit your answers, and hopefully you participate.
Can you go back to the stable diffusion slide? Can you give me like little more context or like examples when you refer to like noise? Like noise. What do you mean by like prompt is something like you're giving as an input, right? Like where is this noise coming from? Where is
it's
all the
literally
knowledge it gathered.
It's literally a matrix of random numbers with Gaussian distribution.
Okay.
That's it.
So it's like
It's literally noise.
Digital like bits and pieces of data.
Yeah, it's like I know that I want like 124 by 124 image in the end. So I create a matrix of 3 channels of noise.
Okay.
And that's what I pass. And then I tell the model, this piece of garbage should fit this description that I'm giving. So little by little, take me back to the image that it existed. So think of it as you know how artists used to say that the sculptures existed inside the rocks and not them. It's kind of the same idea, but it's a computer.
Sweet. Thanks.
Okay.
That's something new, like.
Yeah. I find again it's a very creative way of generating images. Any more questions? Well, I hope you found it interesting and you learned something today. Thank you.